So let's consider application of Gauss's law to a conductor. Now, up to this point, we've been mainly talking about insulating things. For example, we have a sphere and we put charge in it, and the charge stays wherever we put in the sphere. It doesn't move around. So we would say that's an insulating sphere with charge embedded in it. Now, let's say we have a conductor and we put charges on there. And so I want to know, how do the charges arrange themselves in the conductor? Okay, so the key is that if you have an electrical conductor, so here we have a conductor, and I put charge on there. So the charge, well, you know that what makes it a conductor, is that the charge is free to move around. So I put a charge and it can move readily across the conductor. An insulator, the charge doesn't move through the insulator, so that's why it insulates. You know, the electricity won't run through it. With a conductor, the charge will move around. So if I put charges on here, a certain amount of charge, then we know that like charges repel. So if I put up a lot of electrons on here, or if I take away a lot of electrons and we have a bunch of positive charge, how does this arrange itself? You know, imagine a bunch of electrons on here. So I have a whole bunch of electrons, and I put the electrons on here, and they're all going to start moving around. How would they arrange themselves? Now, they all repel each other, right? And so what happens is that if you have a bunch of charge, that the charge is going to be producing electric fields, and that electric field is going to exert a force on other charges and move them. And when they move, that's going to change the charge, the total charge. Even if you have a conductor right here, and even if you just have an electric field in the conductor, what's going to happen is there's already charges that are there. Electrons are going to want to go this way, and that's going to leave that side negative, that side positive. Okay, so if you put charge on there, then the charge is going to repel each other and move around. So your first guess might be that the charges space themselves out uniformly so that they get as far away from each other as possible. Okay, now the problem with that is, that means if you get really close to one of these charges, it's going to have, you know, an electric field either towards or away from it, depending if it's positive or negative. And if you do, then there's charges already in the conductor. Remember, conductors are made of matter. Matter has electrons and protons and so forth. So there's already charges in there. So that's going to move them around until the charges cancel. Anytime there is an electric field in a conductor, the charges will move. And again, if you have an electric field in that direction, then what's going to happen is negative charges will go here, positive charges go there, but then they make an electric field in the other direction, which cancels. So what you can realize is that the electric field inside a conductor is always going to be equal to 0. What's going to happen is, when I put my electric charge on here, it's going to arrange itself in some fashion so that the electric field is going to be 0 on the inside. Well, now let's imagine I draw an imaginary Gaussian surface in here. Well, I know that integral E dot dA is going to be equal to enclosed charge over epsilon naught. Well, right away, I know that the electric field is 0 inside the conductor. Therefore, this integral is going to be 0. So 0 is equal to the enclosed charge over epsilon. Well, quite obviously, the enclosed charge equals 0. So that means there is no charge on the inside of the conductor. So if no matter how I draw my Gaussian surface, there can be no charge in there. Otherwise, there's going to be an electric field. So that means that the charge has to all push itself to the outside of the conductor. So the charge distributes itself along the surface of the conductor. Imagine a conductor in an external electric field. So we have an electric field like that. What's going to happen is that the electric field through the conductor here is going to cause negative charges on this side, positive charges on that side, which make a balancing thing, and it cancels the electric field. So what will happen is there'll be an electric field outside the conductor, but the electric field inside the conductor is going to be zero. Okay. So that's an interesting sort of arrangement. Well, now here's another possibility. Suppose we have a conductor that's hollow. It's got a hole on the inside. So here's my conductor, and I'm going to take some charge, and I'm going to put on the conductor. How does it arrange itself? So you might imagine that some of the charge is on the outside and some of the charge is on the inner hole. Well, if I draw a Gaussian surface right here, integral E dot dA is going to be enclosed charge over epsilon naught. Well, guess what? The integral is still zero because the electric field is still zero here. The electric field will always be zero in the conductor. So that means the enclosed charge is still zero. So that means if I have, a metal box here that's hollow on the inside, then if I dump electric charge on here, all the charge runs to the surface of the box. And so there's no charge on the inner surface. Okay, so this is actually a form of electrical shielding. Imagine your computer. So your computer, the CPU is inside of a metal box. Why? Because you have electronics in here that don't like stray charges, and so if something accidentally happens and a wire touches this, all the electricity is going to be on the outside. So all the charge on the outside, on the inside, it's protected. Number of years ago, there was a traffic accident on Boulevard 26 right near campus, and a car hit a power pole and electrical lines fell down. Okay, it was a wet day. The car slid into the power pole, knocked it down, wires came falling down, draping across the car. Now, power lines are not insulated wires. They're not like the wires in your house. The wires up on the power poles are just bare wires. It would be prohibitively expensive to have that as insulated. So those are just bare wires. So these bare live wires were falling on the car. Well, what that meant was the outside of the car was electrified. What about inside the car? Well, all the electric charge ran to the outside. So inside the car, everything was just fine. Now, the problem is the wire was laying on the ground and was bouncing around, flashing and sparking and so forth, because it was making and breaking contact, and the person inside the car panicked, opened the door, and stepped outside. Well, when they stepped outside, they're no longer shielded by this metal box. And so they ended up getting electrocuted. These metal boxes that you can put surrounding here, or it doesn't have to be a metal box, it could be just screen wire, a metal screen wire that surrounds something you want to protect from stray electric fields. We call that a Faraday cage. It does not have to be, in fact, a solid sort of thing. The Faraday cage can have holes in it, as long as the holes are small enough, or big enough, or whatever, that you don't have a problem. Now, the thing is that the building, the science building that are Northeast Campus, you have rebar in the building, you have electrical conduit, you have water pipes, you have electrical wires, you have reinforcing rods. There's a big metal framework surrounding you, and so that makes the entire building something of a Faraday cage. And that means it's a fantastic place to go during a lightning storm, because you get a lightning storm and the electricity stays outside rather than going through the occupants inside the building. Well, the other problem you run into, though, is that Faraday cage affects radio communication, which are also electric and magnetic fields. And so long wavelength electric and magnetic fields like AM radio will not penetrate into the building because the long waves don't fit through the holes in the window. Short waves like cell phone signals will make it in, but your cell phone actually has to work at much higher power inside the building than it does outside. So those of us that worry a little bit about radiation exposure from the phone will step outside to make a phone call on a cell phone, because you're gonna it's not going to have to work as hard to force the signal out through the Faraday cage. So this is an example here of Gauss's law, and using Gauss's law to explain something like an electrical conductor.